Hello everyone, this is Dr. Young, and in this video we're going to talk about the Mannich reaction. I know it looks like Mannich, but it's the Mannich reaction. And I'm putting it with the amine stuff because you always make amines, but really it's kind of enol chemistry and imine chemistry, that reversible reactions chemistry stuff. So we're kind of going to blend the two together to find a new way to make beta amines. And so let's talk about it. We are here, right? We're down here at the Mannich reaction. We're going to take aldehydes or ketones. We can make primary, secondary, or tertiary amines. The group will most often start with the CH2, but I'll talk about how that can kind of vary in reality. And what you're always going to form is an amine beta to a carbonyl. That's going to be your big tell that you're doing a Mannich reaction. So what do these look like, right? So just kind of to fit things in from that whole slide that I had before, right? We've already talked about primary amines, Gabriel synthesis, Hoffman, check. We already talked about the reductive amination that can make primary, secondary, or tertiary amines, check. And now we're talking about the Mannich reaction, which, like I said, puts amino groups beta, right? So here's your alpha carbon, beta carbon. It puts amines on a beta away from a carbonyl, right? So 2 carbons away. And if you look at this molecule, we'll break this down a little bit more in a second. This alpha carbon now gets attached to the carbon from, in this case, formaldehyde. So this sucker, and then your amine, and again, it can be kind of any amine you want, really. It just can't be a tertiary amine, gets attached. So let's think a little bit more about the components of the Mannich reaction and see what we can do, right? This particular example is the formation of a secondary amine, but we could have made a primary or a tertiary amine also. So the Mannich reaction, I put a lot of notes here because it's an interesting reaction. You're probably going to see it on an ACS test if you're taking that. Definitely in our books and everything. So like I said, it can make a primary, secondary, or tertiary amine. The only limitation is that one substituent on that amine has to have a CH because we're going to use an aldehyde to insert in between sort of that alpha carbon and the amine. That's where we're going to find that thing. The mechanism, which I'll show you in the next slide, is really an enol formation and then an imine formation, and then you have an enol attack an imine. So you combine those two, and then we have what's called the Mannich reaction. For the reagents, right, we're going to have an aldehyde or ketone to start with. Here I have a ketone. So check, right? Here's my ketone. And it does have to have at least one alpha hydrogen, which I do, right? I have 2 alpha hydrogens here. So you need to be able to form that enol is the key thing here, because that's going to go and attack the amine. Like I said, I'll show you in a second here. You also need to have some sort of amine. Again, it can't be tertiary because you got to lose a hydrogen. So I've got an amine. Great. In this case, I have a primary amine. Could have been secondary, or it could have been ammonia. And you need an aldehyde, right? So usually it's formaldehyde. And remember, form means one. It comes from the ants, like formic acid. But that's here, right? So I have CH2O, which if I drew this out would be a carbonyl with 2 H's on it, right? So that's formaldehyde. That's formaldehyde. And then lastly, you're going to have some sort of acid catalyst. So in this case, I just wrote generically H+, but it could be sulfuric or hydrochloric or some Lewis acid if you're getting real fancy. But you need just some sort of acid to help form the enol and help form the imine. And I just wanted to point out here again, right, I kind of started this here, is that it makes beta amines. So if you have a carbonyl and all of a sudden you have a beta amine, that means that you definitely did a Mannich reaction. That's the *1 way that you're likely to see a beta amine get formed, right? So at this beta carbon, now I have an amine, right? It's beta away. It's 2 carbons away. So let's look at this mechanism and see what we can figure out here. So like I said, this is a combination of an enol formation and an imine formation. And then the two combine. So let me show you what I mean by that. I am going to draw out my formaldehyde and my, let me draw out my formaldehyde. Let's just do that here. And I've got my amine. Now, if I compare these two molecules, right, the reason why you're gonna have a aldehyde or ketone to start with, and the second thing, this thing right here, is formaldehyde, right? The second thing, the thing that's going to become the beta carbon, is always going to be more electrophilic than your starting material. And that's because you want your amine to attack it and not the starting material, right? So here I have formaldehyde, which is a very good electrophile. And ketone, which is also a good nucleophile, but not a very good one, right? It's electrophilic. I'll put a good electrophile, but it's not great, right? So the formaldehyde is the better electrophile, which is exactly what you want. The thing that's going to become the beta carbon, you want to be the better electrophile. So it's almost always a aldehyde because, again, they're so electrophilic. So what I'm going to see with this, I'm going to draw two paths, and then I'm going to have them converge here. So first path is just that my aldehyde is going to get protonated by my acid, whatever that generic acid is. And that's going to form, right, our activated, although formaldehyde is so reactive already that this step is probably not actually necessary. But it's going to form your more activated carbonyl, and then your nitrogen can go ahead and attack. And you may notice, again, like I said, this is just an imine formation. So if you already know how to form imines, then you're going to be set. All right, so now you have an OH. Now you have an N with a nitrogen and this cyclopentyl group. Sorry, no lone pairs on that nitrogen, but a positive. We're going to have a proton transfer step. I'm just going to write PT for proton transfer, right? The nitrogen's going to lose its lone pair, or sorry, lose an H. The OH group is going to pick up that H, so I'm just going to redraw that with the hydrogen having moved. All right, so I just moved the hydrogen from the nitrogen to the oxygen. I could have drawn out in two steps, but if you write proton transfer, I'm totally fine with that. And then lastly, you're going to have, right, the lone pairs drop down from your nitrogen. You're going to kick out your water so that you get this iminium. Right, it looks like an imine, but it's still charged. Probably going to stay charged since we're in acidic conditions. That's one part of the mechanism, right? That's one part of the mechanism there. Now, the second part of the mechanism, and I'm going to draw this kind of separately here, is what's going on with your starting material, right? That parent thing with the phenyl. So let me draw that. Remember that you have that acid catalyst. So I'm going to go ahead and protonate this sucker. It's positive. And remember that this is part of how this enol, again, this is not a big K value or anything. You don't form a ton of enol, but you form some. But if you form this enol here, right, where this H, one of these H's can leave, and then the electrons go up here, you regenerate that acid catalyst, right? So here's your H plus again. And now you have a little bit of enol that has been formed. All right, so you got a little bit of enol. Now, what's important about that is that now your enol is nucleophilic here, right? So now it's nucleophilic because that's where the negative charge builds up, right? Remember, you can drop electrons down from that OH, and then that alpha carbon becomes negative. Actually, I should probably draw that. Let me draw that to make sure that we're all on the same page here. Right, if you draw the resonance structure of this, it looks like this, and I'll draw the resonance arrows in red here. So where the electrons drop down, those kick out, right? That makes this resonance structure. But like I said, that alpha carbon, right, is nucleophilic. It's got a part of a negative charge on it. It's got some electron density on it, right? I drew a lone pair in the second contributor. So what happens now is that this thing's nucleophilic. My iminium ion, and I'll draw iminium over here. My iminium ion is electrophilic at that carbon. And so what we see is that the negative charge then goes, attacks that carbon, kicks the electrons back up into the nitrogen to make it neutral, and then we've basically got our product. We're one step away from our product. And I honestly have, oh, well, I'll draw it up here. I'll draw it up here. Here's what that sucker is supposed to look like. I'm going to draw pH instead of the ring to kind of save myself some room. So pH, double bond O, still has positive, the hydrogen on it. But now this is attached to the CH2, right? H and H, and the nitrogen that had an H and now has that cyclopentyl group. Like that, right? Reversible step. And so I just made, right? I just made this new bond right there. And then the very last step is just that the hydrogen leaves to regenerate your acid catalyst. And then boom, you get your product. And that's your product. So I've made that right. You don't see this CH2 anymore because you just stopped drawing them. And the NH is still on there. And then the CH2 and that cyclopentyl group. So that's the mechanism, right? It's actually kind of two separate parts, right? You have to start with part A and then part B, and then they sandwich together there near the end, once you have the enol, once you have the iminium. Now to kind of emphasize some things here, right? Let me do this. I guess I'll just do this in purple since it's already in purple. This, whatever your aldehyde piece is, that's this piece right here, right? That's what becomes the beta spot. That's the beta thing. Come on, there you go. That's the beta thing. So that aldehyde had two H's on it, which is why that beta carbon has two H's on it, right? Because the O is out of here. Always on your carbonyl, your aldehyde or ketone that you have that has the one beta hydrogen, right? That's the new thing. So that alpha hydrogen attaches to whatever that aldehyde or ketone was. And then, of course, your amine here, that piece is then attached to that beta carbon. So that's that piece, right? So here's how you attach the things, right? You take your carbonyl to the alpha spot, you add whatever the aldehyde piece was minus the O's, and then you add that nitrogen piece to that. So that's the kind of ordering that you do. So let's look at some examples. Here's some possible amine targets, right? And again, the big thing here to keep in mind, right, is that we have to have beta amines. So if I look at this first one, here's my carbonyl, here's my alphas, here's my beta, and sure enough, on the beta carbon, I have an amine. So this is a possibility. I could do that. Here, I don't even have a carbonyl, so that's out. Here's an alpha carbon, here's a beta carbon, that works out. Here I have a carbonyl, here's an alpha carbon, alpha carbon. This is an alpha, right? So that's not going to work. Again, it has to be beta, not alpha. And then here I have no carbonyls, so that one's out. Also for the aniline. Can't make aniline this way. So really, the first and the third ones are the only ones that I could make through a Mannich reaction. And if I wanted to make them from a Mannich reaction, what it would look like, what I would do is to backtrack, I would say, okay, well, I have my amine. Sorry, I have my amine. It looks like it's just a methylamine, so I'm going to go ahead and draw that it's just a methylamine. So CH3, NH2. I have this middle piece right here where the beta carbon is. That just has hydrogens on it. So I know that that's just formaldehyde. And again, formaldehyde is the most common example that you're likely to see. Really, it can be any aldehyde, but formaldehyde is the most common example that we see in first year organic chemistry. And then I have the rest of this piece here, which should be the carbonyl compound that I added it to. So these, and then plus, right, plus a little acid catalyst, some acid catalyst. So here's the components that I would need to mix together to do the Mannich reaction to make that beta amino compound. Not amino, but amine. If I wanted to do it for this one, I would do the same sort of procedure. Right, it looks like the amine that I'm adding is a diethylamine. So then I need to add that. It looks like, again, the beta carbon just has two hydrogens on it. So I'm going to add formaldehyde again, CH2O. And it looks like this is the rest of it with the alpha. So it looks like I just need acetophenone, or this methylphenyl ketone thing. And again, just some sort of acid catalyst, so let's just say HCl. So those combined would make that amine up there. Let's look at some more examples. Here's 4. They all work. I recommend that you pause, try this with yourself. Remember to find the alpha carbon on your starting thing. Probably you're going to add CH2 unless there's a different aldehyde there. And then comes your amine. So go ahead and pause, take some practice. Okie doke, so here we are. So I've got this ketone here. There's probably more room on the left than the right, so I'm guessing that's going to be the major product, given that the enol has to attack something, even though they're more stable enols on the right-hand side. So you could get 2 products for this. I'm just going to draw one of the products. So I'm going to draw my carbonyl compound. I see that that's the alpha carbon. So now I'm going to add my CH2. So here's my CH2, right, from the formaldehyde. And then I'm going to add the amine, which apparently is a diethylamine. So that's what that thing should look like, and I'm just going to clean it up. I'm not going to draw the CH2 anymore. Draw the nitrogen. Here's my ethyl, CH2, the alpha carbon, carbonyl, and then that sort of isopropyl piece. That's what the molecule should look like for my Mannich reaction. If I did the same thing for this one right here is my alpha carbon, so I'm just going to go ahead and redraw that whole molecule. My carbonyl, in this case I also have formaldehyde, so I know it's just a CH2 right there. And in this case the nitrogen is a propylamine. So I just add that propylamine, right? I had to remove one hydrogen because it loses one hydrogen during the mechanism, and that's what it should look like, right? Again, where that is my alpha carbon, here's my beta carbon that came from, it's a terrible beta. There you go. That's a slightly better beta. But that beta carbon, right, again, came from the formaldehyde. And then you have your propylamine. Now here we're doing something a little different. I'm trying to go backwards here. So here's my carbonyl, here's the alpha, here's the beta, and then my nitrogen. I see that the nitrogen's a propylamine, 1, 2, 3 carbons, 1, 2, 3 carbons. So that checks out. That's that piece. I see here that this actually isn't a CH2. This is a CH with a phenyl. But that makes sense given this, right? Because here I have a phenyl and an H, so that checks out. Which means the only thing I need to do is then just draw what the rest of this is. So I just need to draw that as my starting material, right? Because it must have been that carbonyl. Apparently this was the alpha carbons that got taken off. The aldehyde in this case was benzaldehyde with that phenyl group and then the carbonyl and the H, that aldehyde. So you don't have to always use formaldehyde again. You're most likely going to see formaldehyde, but it doesn't have to be formaldehyde. And then you add the amine. This last example, we need to do the same sort of analysis here. I've got a alpha carbon, I've got a beta carbon. That beta carbon looks like it only has H's on it, only CH2s. So it must be that I did add formaldehyde in this case. And I'm going to add some sort of catalyst. Pick what you want. I'll pick sulfuric acid. And the amine in this case was a pyrrole. So I'll add that cyclopentyl amino looking thing, right? That cyclic amine right there. And that's how you'd figure out those. Hopefully this helps you out with the Mannich reaction. Do lots of practice. Let me know if you have any questions. Happy studying.